You just gotta love that tune, don't you? So we're going to be looking at what are called constrained extremum problems. And the idea is this. Whenever you graph a 3D surface, whether it's a surface or a solid in three-dimensional space, those extend indefinitely. Not so much the case for 3D solids, but 3D surfaces typically extend indefinitely. And in function format, they would be given usually as z equals f of x comma y. And so you pick an ordered pair from the plane, you plug it into your function involving the variables x and y, and you get a z coordinate. And this produces an ordered triple, x comma y comma z. And typically what you get is a 3D surface, such as the one that you're seeing here in wireframe. All right, so this would be an example of at least a chunk of the 3D surface. It would extend indefinitely in all these directions, but what we're doing is we're subjecting it to a particular what's called constraint. And in this section, the constraint is going to be right here, that the norm of a vector x is equal to 1. Now, if we assume the Euclidean dot product to say that the norm of a vector x is equal to 1, let's assume that x comes from the plane, so it has the components x comma y. To say that the norm of the vector is equal to 1 is to say that the square root of x squared plus y squared is equal to 1, which if you square each side, this implies that x squared plus y squared is equal to 1. And if you think geometrically about what this equation produces, this produces the unit circle. Okay, the circle of radius 1 centered at the origin. Long story short, to say that the magnitude of a vector is equal to 1 means that we're constraining ourselves to the unit circle. Now, geometrically, what in the heck does that all mean? Well, it's the reason for this chunk of a surface. This chunk of the surface sits above the unit circle in the plane. All right, and we have the unit circle kind of sketched out in this diagram. And our constraint of this unit circle allows us to find a point that's closest to it, that's on the rim of this chunk of the surface, and a point that's furthest away from it on the rim of this 3D surface. So if we focus ourselves on the rim, which I just outlined in this pink color, that rim is sitting right above the unit circle, and just by its geometry, there appears to be a point on this rim that is as close to the unit circle as possible, and that appears to be, let me use a different color. One of those points appears to be right here. And what I mean by as close as possible to the unit circle is that this is the minimum distance. So that would be the minimum distance from Z to the unit circle. Also known as a constrained minimum. There appears to also be a point that is furthest away from the unit circle. It appears to be right there. And by furthest away, I mean it is the maximum distance from Z to the unit circle. Okay, so if we were to connect that point with the unit circle, the length of this line segment would be the longest of all such line segments that we could create. And that is known as a constrained maximum. Right. Did I explain that okay? Is that making sense? Everything so far? Any questions about it? All right. Well, if we have a function in x and y that is a quadratic form, we know that we can write the quadratic form as x transpose ax, where A is a symmetric matrix. And we will actually be doing that again in this section because we're going to try to maximize or minimize a quadratic form subject to this constraint of the unit circle. And so we'll be working with symmetric matrices again. And what's really cool about this section is that these the eigenvalues of the symmetric matrix actually give way to these minimum and maximum distances. This theorem says that if A is an n by n symmetric matrix whose eigenvalues are an order of decreasing size, given by this chain of inequalities, so given this chain of inequalities, lambda sub 1 would be the maximum eigenvalue, so it'd be the largest of them all, and then lambda sub n would be the smallest of all the eigenvalues. If this is the case, then our quadratic form, x transpose ax, will have a maximum value and a minimum value. In plain old English, this means that max and mins exist. Furthermore, the maximum value occurs at a vector corresponding to lambda sub 1. Let me write that in this light blue. So this eigenvalue lambda sub 1, the leading eigenvalue in this chain of inequalities, that gives way to an eigenvector that produces the maximum value of that quadratic form. The minimum value will occur at a vector that corresponds to the smallest of the eigenvalues, lambda sub n. One thing that I want to note alongside of this is that we're subject to the constraint that the magnitude of the vector x is equal to 1. Geometrically, we're subject to the constraint of the unit circle. That means our surface is above the unit circle. And so when we produce any of these eigenvectors, which that's what they are, we need to make sure that their norm is equal to 1. So I'm going to say the norm of each eigenvector has to equal 1. And the reason for that is because of our constraint. Another thing is that there might be more than one vector that produces the maximum and minimum values. Okay, so it's important to note what it doesn't say as well as what it does say. The maximum value occurs at a vector. It doesn't say it occurs at the vector, all right? So if we have multiple eigenvalues that we can form that have a norm of 1, then we want to consider all those eigenvalues. And the same thing would go for the minimum value, right? And I meant to say eigenvectors. So let's get to an example, show you what this is all about. It says find the maximum and minimum values of the quadratic form subject to the constraint x squared plus y squared is equal to 1. So again, what this means is that the norm of a vector x is equal to 1, i.e. the unit circle. And to start this out, this quadratic form is what I'm going to set z equal to. So this is a particular function in two variables, x and y, that also happens to be a quadratic form equation. And what we can do, because it's a quadratic form, is we can write it in the format x transpose ax. And let me give you a moment to do that. We'll go over it, and then we'll proceed to the next step. All right, you guys ready? So x and y, and then remember the coefficients of the square terms go along the main diagonal, and then the coefficient of this cross term needs to be divided in half so that we can get a symmetric matrix. Now what we want to do to help us figure out the eigenvectors that produce the maximum value of z subject to this constraint is we want to find a basis for the eigenspaces of A. Okay, so this is like a step 1 where we rewrite it in quadratic form. Step 2 is going to be to find, and I'm going to say this, find an ON basis for each eigenspace. That means we're going to have to find the eigenvalues of this matrix A, which I'll provide to you, and then we'll work on the basis. Lambda I minus A will look like lambda minus 5 along the main diagonal, negative 2's off the main diagonal, and when you form the characteristic equation det lambda I minus A equals 0, you end up getting the eigenvalues lambda equals 3 and lambda equals 7. Let's start with lambda equals 3. And what we're starting here is the calculation of an orthonormal basis. So when we plug 3 into lambda I minus A, we're going to get negative 2, negative 2, and don't forget we augment it with the 0 vector. Bottom row will be negative 2, and 0 as well. The RREF version of this matrix goes as follows: 1, 1, 0 in the top row, and then 0, 0, 0 in the bottom row. First column associates with x, second column for y, and it looks like x corresponds to a leading 1, which means that y would have to be our parameter. Now this will give way to a basis vector with the first entry of negative t, second entry of t, which we can factor the t out to get negative 1, 1. And so a basis would consist of the vector negative 1, 1. But is this the appropriate basis to use?
1.
So this vector doesn't have a norm equal to 1. I'll say it this way. The norm of that vector x does not equal 1. So because the norm of this vector doesn't equal 1, what we're going to have to do is unitize it, which essentially turns it into an orthonormal basis. And you would divide each component by this vector's magnitude, which is radical 2. So the first entry would be negative 1 over radical 2, and the second entry would be positive 1 over radical 2. Now, I'm going to make mention of something else. This actually isn't the only basis vector that has a norm equal to 1. Alternatively, what you could do, and I'm going to include it with an and statement here, if you were to choose t, our parameter t, as negative 1, then that would change the sign of our two entries of this basis vector, but it would still have a norm equal to 1. So in other words, this vector right here does have a norm equal to 1, so it satisfies our constraint of being in line with the unit circle. But there's another vector x that has a norm equal to 1, and that would be the vector that we can form by changing the signs of these two entries. So positive 1 over radical 2 and negative 1 over radical 2. So in terms of the eigenvectors that satisfy the constraint, we've got two of them. We've got this basis vector, and we also have this basis vector. All right, and I'll talk about the significance of each of these basis vectors. But before that, I would like you folks to take the next few minutes or so to find basis vectors for lambda equals 7 that each have a norm of 1. All right, I'll go ahead and flesh out the details of my basis vector solutions. Plugging 7 into lambda I minus a, you get a first row of 2, negative 2, 0. Second row, negative 2, 2, 0. Our REF version of that matrix, 1, negative 1, 0. Then a row of zeros at the bottom, x and y. X corresponds to the leading 1 again, so y equals t. This time the basis vector would both consist of entries of t. Factor that out, and we get a basis vector with entries 1, 1. And so a basis vector for this eigenspace is 1, 1, but unfortunately it's a basis vector with a norm that is not equal to 1. So we proceed to form an orthonormal basis by unitizing this. Which amounts to taking each entry, dividing it by radical 2. This will ensure that the norm of the vector is equal to 1. But there's another basis vector with a norm equal to 1. And that would be a vector that has the opposite sign of each of these entries. So negative 1 over radical 2 and negative 1 over radical 2. Okay, that's another vector, basis vector for the eigenspace that has a norm equal to 1. Now, you guys want to see? Yep, go ahead.
Sorry, I just wanted to ask that where do you find that radical 2 from?
Oh, okay, yep. So this right here, if we do the norm of 1 comma 1, we square the first component, add it to the square of the second component, and then we square root. So it's the Pythagorean theorem. So we square each component, so 1 squared plus 1 squared, and that will give us 2 inside of the square root.
Oh, okay, I got it now.
Yep.
Thank you.
No problem. All right, so let me show you guys something cool. This is the stuff that really excites math nerds like me. I'd like to use one of these basis vectors, and I'll make this a little note. Let's use the basis vector from lambda equals 3, which has the components negative 1 over radical 2, 1 over radical 2. If we plug this into our function z, the original version of it, we would have 5 times negative 1 over radical 2 squared plus 5 times 1 over radical 2 squared plus 4 times negative 1 over radical 2 times 1 over radical 2. You'll be amazed at what this simplifies to. What I'm going to do is square each of the components, and then I'll also form this product with the product of the two components. This is going to be 5 times 1/2 plus 5 times 1/2 plus 4 times negative 1/2. Can you guys simplify this expression and type in the chat what it simplifies to? Any offers as to what that simplifies to, folks? 3. You got it. Now, haven't we seen this 3 before? What's the connection with our value of z and one of the results from earlier in this problem? This is one of our eigenvalues, isn't it? In fact, 3 is the smallest of the two eigenvalues. Z equals 3 represents our minimum value, min value of z under the constraint of the unit circle. Now, if you were to do this with one of the basis vectors from lambda equals 7, you would get the maximum value. Let's take a look at that. Let's use 1 over radical 2, comma 1 over radical 2. That'd be 5 times 1 over radical 2 squared plus 5 times 1 over radical 2 squared plus 4 times the product of those two components. Go ahead and simplify this all and tell me what you get. All right, let's verify that. So it'll be 5 times 1/2 plus 5 times 1/2 plus 4 times positive 1/2. So that's 5 over 2 plus 5 over 2 plus 4 over 2. That's 14 over 2, which gives us 7. And lo and behold, with a basis vector for the eigenspace corresponding to lambda equals 7, when we plug that basis vector in after it's unitized, we get the eigenvalue, and this doubles up as the max value of z. Yep, go ahead with your question.
Earlier you had changed the sign so that there was a basis, an orthonormal basis, an alternative one with the sign changed. What exactly is the purpose of doing the sign change? It wouldn't make a difference, would it, on the outcome given the polynomial equation by squaring it? Doesn't that sort of nullify the effect of changing the sign?
Well, what we're looking to achieve here is finding all the vectors that would give us these two values. So you're exactly right. If even when we change the sign to get the secondary basis vector, it doesn't change the outcome of z. What we're doing by finding these basis vectors is we're trying to figure out like all the solutions that would give us the maximum and minimum value. And so if we only keep the first unitized basis vector, we've only come up with half of the vectors that would give us the minimum of 3 and half the vectors that would give us the maximum of 7. So we're trying to collect all possible solutions that would give us the same outcome.
Okay. And all that's involved is just changing the sign, or
Yeah.
is there more involved to identifying additional orthonormal basis vectors?
Right. So you would only need to change the sign, and it's kind of a shortcut trick. Think about our parameter t. Oh, bad color to use. If this value of t was different from 1 or -1, the norm of our basis vectors would not equal 1. So like if I were to multiply the first basis vector by, say, 5, then the second basis vector would no longer have a norm of 1. So basically, in order to get a second basis vector that still has a norm of 1, the only possibility of doing that is just to change the signs.
Okay.
Because any value different from 1 or -1 is going to impact the norm of that second vector. So by changing the signs, we get a different basis vector, but it still satisfies the criterion that the norm is equal to 1.
Okay, thank you.
No problem. I'm going to go underneath the supplemental problems here. And let's officially answer this problem. It says find the maximum and minimum values. I'll start with the minimum. I'll say min value equals 3. Okay, that's the smallest of our eigenvalues. And I'm going to say this occurs at 2 vectors, x equals -1 over radical 2, comma 1 over radical 2, and x equals +1 over radical 2, -1 over radical 2. The maximum value is given by our largest eigenvalue, which is 7, and this occurs at 2 basis vectors. The first, 1 over radical 2, comma 1 over radical 2, and the other where the signs are changed. And this is how we would officially answer this problem. Now, Joe, I'm thinking about your question some more. Let's do a little drawing here. I'm going to do a two-space diagram. And on this diagram, I'm going to include the unit circle. So let's center at the origin and has a radius of 1. For lambda equals 3, we produce 2 vectors that would be points on the unit circle. The first vector was -1 over radical 2, +1 over radical 2. And that would be right here at 3 pi over 4 on the unit circle. Now, due to symmetry, there's going to be another point that helps us find a minimum value, and that would be on the opposite side of the unit circle. So in this first instance, at 3 pi over 4, we've got negative 1 over radical 2, comma 1 over radical 2. And due to symmetry, across the other side on the unit circle, we'll have another solution. And that point right there would have the coordinates 1 over radical 2, negative 1 over radical 2. And that's kind of like a geometric justification of changing the signs, right? Because the first coordinate of each point are opposites of each other, and so are the second coordinates.
Okay, appreciate the illustration.
Does that help out?
Yes.
All right, cool. Well, if you like that illustration, I got something even cooler. I'm going to drop you guys a link in the chat to this GeoGebra 3D calculator site. Hang tight, my Blackboard likes to freeze when I switch from tablet to laptop mode. There we go. Follow me to this website, folks. And over on the left, you should see a plus sign and the word input. Let's go ahead and click on that. And we're going to type in our quadratic form. There should be a keyboard at the bottom of your screen. Let's type Z equals, and then 5x, and right underneath x, you have a button that puts a power of 2 on it. It's already sketching a surface out for us. Plus 5y squared plus 4xy. So that's our quadratic form, and you can click on the diagram and drag it around. It kind of looks like a paraboloid, but the rim of it looks more like an ellipse. It looks like half an ellipsoid of sorts. But let's go down or go over to the left. There's another plus sign, which means that we have the capability of entering another equation in here. And the equation that I'd like us to enter this time is the equation for the unit circle. That'd be x squared plus y squared equals 1. Now, I believe you can change the color of your graphs. I think if you just click the red circle, no, not that. Let's try this drop down. Yeah, so let's click on these 3 dots right here, and we'll go to settings, and there's a tab for color. I like to use green for it. So if you want to use green, you can do so. So I'm selecting that, and I'm going to X out of it just to see if it changed the color of our, yeah. Okay. Anybody need me to repeat those steps? Okay, so we have both the quadratic form and the constraint entered in. I'm going to get rid of this keyboard just to give me some more real estate here. And you can see that the unit circle is actually drawn as a cylinder, which is helpful because you can see that the cylinder intersects this quadratic form. And I'm going to zoom into this area on the quadratic form. And this is the rim of that surface. So you remember on page 1 of the notes, let me go back to it. I outlined the rim of the surface in this pink color. This is where the unit circle would intersect the quadratic form, should it be drawn as a cylinder. Okay, so that's the rim, and it's on the rim of that intersection that we get our minimum and maximum values. I'm going to our GeoGebra graphs. This appears to be the lowest point of intersection between the cylinder and our quadratic form. And if you look inside of our quadratic form and count the tick marks, that seems to be parallel with the tick mark of z equals 3. And that actually is the case. Now, if we look at the axes from the coordinate plane, that point of intersection, which gives us a minimum value, let's see, I gotta remember which one's x here. Does it have it labeled? Well, either way, one of the coordinates is positive and one of the coordinates is negative. So we're either going to be in quadrant 2 or quadrant 4 in this one. So there's another point of intersection that gives us the minimum value of 3, and that's on the exact opposite side. Okay, so here's another instance of a lowest point on the rim of the intersection, and that's at 3 as well. Okay, so if we had forgotten to change the sign on our basis vectors, we would only get one vector that gives us the minimum value, where in fact there's actually 2 vectors that give us this minimum value. And you can zoom out a little bit. And here's where the highest point of intersection is on the rim. Okay, so the unit circle transformed into a cylinder goes all the way up to here to form the maximum value. So this is where the highest point of intersection between the cylinder and our quadratic form occurs. And that occurs at a point in quadrant 1, okay, in this quadrant. But there's another point in quadrant 3. You can kind of see it right here, that there's another point or another vector that would give us the maximum value of 7. And so again, if we had forgotten to change sign on those basis vectors, we would miss out on the vector that produces this high point. And the coolest thing about this program is that if you click and just quickly scroll to the left and let go, it's not doing it. There we go. You can have it rotate and get you so dizzy that you'll have to get up from your couch, bed, or chair, wherever you're sitting for the Zoom session, and take care of business in the bathroom. But at any rate, I think that's where I'll leave it for here. We can watch that introductory video on Markov chains tomorrow. Do you guys have any questions for me about section 7.4?